No, one of the other organizers gave me this VGA, and I tried it on the test projector, and that worked. I could try another HDMI, though. Now, am I allowed to walk away from the mic, or?
You should talk to the video guys about that. But
Okay.
I think you can, but I don't know what they're doing as far as that goes.
Okay. 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 No, it picked up, but it was in the wrong mode when you plugged it.
So what I did, I just unplugged it, plugged it back in.
Okay. Okay. Great.
Yeah, no pressure, right?
Yeah. Where's my mouse? There we go. Displays. Okay, great. Hello, everyone. Hello, everyone. Who here has seen the movie Dude, Where's My Car? Who here has not seen the movie Dude, Where's My Car? Okay, so for those of you who have not seen the movie, I'll give you a quick introduction. It's a refrigerator full of data, no memory, refrigerator full of pudding. Can you hear me now? Okay. So two guys wake up in the morning to a refrigerator full of pudding, memory of what happened the night before, and no idea where their car is. Their car contains their gifts for their upcoming girlfriends. So as the movie begins, the two guys try to retrace their steps from the night before to find their car, to get the gifts to give to their girlfriends. As the movie progresses, they actually get caught in the warring factions of aliens. Because the night before, they come into possession of a device called the Continuum Transfunctioner. And by the end of the movie, the balance of the universe hangs in their hand. So the premise for this presentation is actually quite similar. You wake up in the morning to a refrigerator full of data, no memory of what happened the night before, and no idea where the person is who you hired to analyze that information. What do you do? How do you get going? And how do you get going quickly? My name is William Stevenson, and I work for MaxMind. We provide geolocation services. We also screen the riskiness of transactions, approaching about $1 billion a year. I wanted to apply machine learning to help predict the riskiness of these e-commerce transactions. So I tried taking a massively open online course. I dropped it after the first week. The professor had billed the course as any diligent student can make it through the material, but later when I read the fine print, he said that you needed to have linear algebra, Bayes' theorem, and a solid grounding. It's a little bit different than any diligent student can make it through the material. Eventually, a colleague recommended the book Machine Learning with R. As I went through the core of the book in about 3 weeks, as I learned each algorithm, I applied it to the problem I was trying to solve. And then in the final 2 weeks, I was able to evaluate the final candidates pretty thoroughly before putting one forward for integration into production. So I was very, very frustrated with existing pedagogical modules. I wanted to learn this. So my hope is that by the presentation, you'll have a map of the territory around machine learning and a compass as to how to navigate that territory. This presentation will need resources. My hope is that you'll hit the ground running and your learning will. There'll be 3 main parts to the presentation. Concepts and practice. In terms of theory, I was a philosophy major, so let's begin with a question in learning. This is Nork back from the 1950s. Find the track of knowledge. If we push this a little bit farther, it gets a little self-referential. So let's actually look at some examples. For those of you not from the United States, this is American football. And over here we have the defensive linebackers. Over here we have the offensive. And the offense has a play, and the defense's job is to stop that play. It's not telling the defense what they're going to do. So the defensive linebackers have to read the play before it happens without knowing what the offense is doing. This actually takes incredible intelligence. Imagine trying to program in the backseat of a Jeep, driving off-road, without the drivers dodging 500-pound boulders. What they're doing under incredible physical stress actually takes incredible intelligence. Roofing and construction. This is another example of learning. After you learn the basic grammar, then knowing how to build a building is another form of learning. Music, when we learn how to play an instrument, Bach might write a fugue, and then when we find the structure in it, a theme, that's an example of learning the pattern that somebody else created. But in learning to play a musical instrument is another form of learning. Interaction, reading facial cues, social intelligence. More typically, formalized learning by a math professor. So what do all of these have in common? I'd actually say 2 things. They all have structure, and they all have pattern. Let's look at another example of a classic example of learning to drive the point home. The motions of the planets. Does anybody know who this is? Close. Tycho Brahe. And this? Johannes Kepler. So over a 30-year period, Tycho Brahe took hyper-accurate measurements of the planets with a device like this. He collected data. This is actually real data from 1599. Let's party like it's 1599. And anyway, after he inherited his data, and Kepler made some of his own observations also. And eventually, Kepler was able to reduce 30-plus years of data to 3 laws, the first 2 of which are that the motions are an ellipse with the sun at one of the foci, and they sweep out equal areas in equal amounts of time. Many people say that Tycho Brahe and Johannes Kepler started the scientific revolution, but I actually have a slightly different take. To me, they were 2 of the first data scientists. Tycho Brahe's ability to take such accurate measurements was unprecedented in human history. And to analyze it was one of the greatest examples of hacking on data in the history of humankind. And it changed our understanding of our place in the universe forever against great odds. There's a lot of pressure politically and religiously a different model of how the planets moved. But Kepler was able to reduce all of the information to a simple model. Learning is a compression algorithm, much like gzip or JPEG. JPEG tries to find similar regions of color and reduce them to a smaller amount of information while still preserving the overall integrity of the image. With gzip, it tries to do something similar, but it's lossless. It has an ability to go back to the original Both of those are taking a large amount of information and making it smaller. We actually do something very similar. Learning is also a model, or as Matisse would say, this is not a pipe. We create this model so we can manipulate it more easily and understand it, to turn it around. Finally, learning is also a function, and I mean this more generally. It could be a linear equation, or it could also be a set of conditions. We're basically mapping things to another when we learn. If we take a lot of data, like the linebacker, about the offensive positions, he's going to try and reduce that into the plays that they might be making. It's basically a map-making function. So more generally, learning creates a function to model the structure and information. This is true of both humans and computers. So the machine learning, we're actually using the computer to find the structure and information. As I started working on this presentation, it occurred to me that learning is actually a meta-function, is a function that knows how to. So let's move from theory into concepts. What kind of machine algorithms actually exist, and let's learn a little bit more about practically machine learning. Generally, there are two branches: supervised learning. In unsupervised learning, we're trying to describe the information, find clusters or like groups, like what products might somebody buy at the same time. With supervised learning, we have a truth like tomorrow or not. We try and create a model that's going to predict something in the future based on historic information. Within supervised learning, we can predict a class, like small, big, or large. We can try and predict a numeric value more continuously. We're going to focus in this presentation on supervised learning. Algorithms. Let's look at a few different algorithms. Regression. So here we have distance from town center in meters, and up top we have the liters of ale. These are the points. As you can see, as we get farther from the town center, the cost of beer. At about 100 meters outside of town, we only have 2 pounds in our pocket. How far do we have to walk before we can find beer that we can afford? So one way to do this would be to try to draw a line that generally describes information, these points. So we go like this. The way we're creating the line is we're trying to minimize the distance between each point in the line. This is the error between each point, and the different ways of actually sort of error, but the general intention is the same. So basically, 900 meters to get our beer that we can afford on average. Does anyone here speak Spanish? Okay. Dime con quién andas y te diré quién eres. Anybody? Tell me who you walk with, and I'll tell you who you are. So we have longitude and latitude. We have more points. The bluish fiber optic internet, and the red ones just have cable internet. So if we move into this house right here, we want to know whether or not we're likely to have cable internet or Fios. We can find people that are closest to us, and based on their availability, we can determine that we probably have cable. Perfect, because this point right here, that would probably get classified as red, which would be a wrong classification in this case. But generally, it'll probably hold up decently for this data set. So we have wind speed in kilometers per hour. We have temperature in degrees Celsius. We have another set of points. This time is whether we should fly a kite or not to fly a kite, like Mary Poppins. So what decision trees do is they use entropy from information theory to divide the data set into homogeneous regions. So if you see that if we draw this line here, anything with a wind speed greater than a little over, we'll say is don't fly a kite. And it stores, so every time it makes a decision, there's either another decision, another parent node, or children, and the children are class, the predicted class. If we're above roughly 8, don't fly a kite. If we're less than it, we're going to make another decision. We're going to keep dividing the data into smaller and smaller groups until we get them as homogeneous as possible. So we go up here, 34 degrees, probably won't. Pretty cold, probably won't fly it either. There's one misclassified, but maybe it was right here. So generally, entropy to find which divisions carry the most target class, we've basically been able to find the box in the middle. Those are decision trees created by a guy named Ross Quinn of Australia. Naive Bayes. So if we have an email message with Viagra in it and has an 80% probability of being spam, we have an email message, we generally, if the word free occurs in an email, there's a 30% probability of being spam. We combine them together. What's the joint probability with both Viagra and spam? Both Viagra and free is spam. Emails we've already received, 100 in total, and 20 of them are spam. The word Viagra appears 5 times, and 4 of them are spam. The word free appears 10 times, and 3 are spam. That's how we got our 80 and our 30%. So what we do is we make a likelihood table. So we have the number of, spam message, Viagra appeared 4 times. The 80 non-spam, the hams, Viagra did appear once. And we did the same thing for free. Probability of spam given, if we added the probability of spam for Viagra and free, and we divide it by the probability of spam of Viagra and free plus the probability of ham of Viagra and free, we'll get the probability that our message is spam. So these two equations, probability of spam given Viagra and free, to the probability of Viagra given spam times the probability of free given spam, the probability of spam given the whole data set, probability of Viagra divided by the probability of free. And same somewhere for the one below with ham. We actually get rid of the denominator because it's going to cancel itself out. So we end up with this. We just plug in the values from our likelihood table. We get these two values. We're going to divide the top one by the top one plus the bottom one. It's an 87.27% that our message is spam. Support vector machine. We have more data, income and age, Republican and Democrat. So I don't know if but people say as you earn more money or you get older, you're more likely to be conservative. So if we have 2 new points, we want to classify them. We could try and divide this space into 2 homogeneous, a little bit different than decision trees, and it only makes one separation. Zero line. Generally, the upper region would be red, and the lower region would be blue. So we classify. So choice. When we're working with machine learning, we have a target value, and that target value is a function of the independent variables. So we want to ask ourselves, what is it a function of? And also, with our target value, there's both a class target, like small, medium, and large, or continuous. So the things that our target is a function of, what are called features, this is given in machine learning. And one thing you want to think about also is the relative scale of your features. Like if you're doing nearest neighbors, for example, and you're calculating distance, the scale of your features is going to really matter because one thing's from 0 to 100, another thing's from 0 to a million. The feature that has the 0 to a million scale is going to have a much larger distance and it'll throw things off. So you actually have to scale your values before you use that algorithm. So getting a sense of your data is really important before you're trying to create a model. Also in the real world, we often have sparse data. We might have missing values, and how your algorithm handles them is really important. Some can handle them better than others. Sometimes they're sort of tricky things, like you could sort of, if you're missing a value, you could code it with the mean value, but it's not great. Another thing, how much data do you have? If you're sort of that someone's generated in a lab, you might have in the thousands. Generating online data, you probably have in the millions. So also depending on the number of features. So some algorithms handle a lot of data more than others, especially in terms of. So I sort of created this chart to summarize what I just talked about in terms of what they predict and the features they can handle, how they handle undef values in big data, and whether you need to scale them or not. I added one right here called model trees. They're actually a hybrid of decision trees and regression. Class at the leaves, they actually have a regressor just for the examples in that homogeneous region. So as I said, there's some tricks you can do. If your data, but you're using Bayes, so you want a continuous value, but you're just only giving spam or ham. Usually the classifiers will predict the probability of the class. If you only need something from 0 to 1, you actually still use that to get a numeric value, even though it's predicting a class. So as you get into it more, there are sort of some tricks you can do to get different algorithms. So in terms of practice, let's work through a real-world example. Ryan and Mel to build their dream house. In the town that they're living in, there's no undevelopable land, undevelopable. So they decided that they want to buy a parcel from existing property. But it's probably going to take 2 or 3 years before they actually get to move into their house between working with the architect and doing the construction. So part of the thing, they want to know what's their holding while they hold this plot of land. And because the plot doesn't have any history on it, because it's being cut off from an existing parcel, there's no use to know what this is going to be. So Ryan's surfing the internet one night, and it turns out that the town that they live in posts their entire housing assessment data online, and it's already structured. So here we have that data set. We have the parcel ID, the address, the land value, the building value, the total value, which is just together. We have a neighborhood code, that's sort of a number that quantifies how desirable the neighborhood is, like how wide the sidewalks are, maybe what the average lot size is, how far it is to the local school. We also have the lot size. So again, land is our target value. So that's our target value, and we're going to wonder what it's a function of. So I think that we're going through a process right now called feature generation or feature selection, and I feel like total is sort of irrelevant because we already have land to just sort of confuse things. So just out of gut instinct, I'm going to drop total. Now we want to start exploring our data. In terms of min, max, mean, we could also look at standard deviations or plot histograms to sort of get a sense of information. Is it skewed to one side or another? What are the relative ranges? And when you're doing something like this, you're not really trying to find anything. And one of the things that I love about machine learning is that in some ways it's sort of like very really using the front of your mind to sort of go for the answer. In other ways, it's sometimes like being a blank canvas, and you're sort of trying to figure out what picture is it going to be. It's like finding a quality to this. It's sort of like those in the shower moments, you can actually cultivate those. So it's really important to go towards it and be analytic, but also rest and relax and let the answers come to you. So when you're doing sort of the feature exploration, you're not really trying to figure anything out. It's more like you're trying to let the information come to you. Transparency a little bit so you can sort of see that. So basically, it's almost like looking at an X-ray. So there are these clear lines here and here. Those are sort of gradiated. So I don't really know what it means, but there's clearly some structure when we plot land value as a function of lot size. Now, before we looked at the distribution of them, now I'm plotting individual variables against our target value to see what is there. Let's do land value versus the neighborhood code. There's kind of like one. So it's I don't know 100% what it means land value, and like looks like a blob. And then I should reduce the opacity of the points to see if I could see any underlying structure. And we are sort of getting these lines here. It just sort of seems a little funny to me. I decided let's drop building value. None of these. And I don't know how this occurred to me, but I thought let's try and coordinate. I thought maybe physical location also. So luckily our government has an API to geocode locations. So but you're only limited to 1,000 rows per file. So you could sort of wrap this in. You can actually just do it in Bash and wrap it in a for loop. So here we replace the address with the latitude and the longitude. And if we plot the latitude and longitude and we color code the land value where red is lower and sort of green is higher, we can clearly see that there are these certain regions in the town lower and higher land values. So, and then I was talking before about sort of that duality of being an artist and being an analyst. I don't know how this came to me. It was just sort of looking at the data, and I thought, hey, maybe this would be interesting. And I think I'd read about Tiger Geocoder months ago. But it just sort of came to mind as worthwhile doing. And it seems like it has a lot of value. So we're going to say that our land value is a function of lot size, the neighborhood code, the latitude, and the longitude. So this is called a training set. In ours, we have about 5,400 examples. The land is our target. These are our features. And the parcel ID is a tag. It's kind of like a primary key. So you need for each row. It's really helpful in debugging. If you ever wanted to figure out, say a particular prediction was off, the parcel ID could help us sort of look at particular examples to get a better sense of how it's going wrong. So A, B, C, D, and E are just our examples. So now we have to figure out which algorithm are we going to use to analyze this data. So right off the bat, we can knock these guys off because they only predict a class, and we want to predict a continuous value. so they're not going to work for us. So now we'll let regression and support vector machine. I don't want to work because it fit a single line to the entire data set. As we saw when we lot size versus the land value, there are a lot of sort of parallel lines. So I think regression is going to have a hard time representing that. So it almost feels like we really want a hybrid between regression and decision trees. We'll see that in a sec. So anyway, so there's tree and support vector machine. I feel like there are more regions than the SVM. My gut is let's just do model tree. And there's not, just because you try one algorithm doesn't mean you can't try others. So this is the first one I thought would be good to try. So I'll go on a little bit more why. So as I said before, we have the sort of multiple parallel lines. So it looks like regression in some ways, but it also feels like a decision tree in terms of these different zones on the map. So it seems like a hybrid between the two. So model trees seem like a perfect fit. So there's a guy named Ross Quinlan out of Australia. He created one called C50, which is a decision tree. He also created something called Cubist, which is sort of the one that comes after C50, because Cubist can only predict a class, and Cubist can predict continuous values. So, but his work is really interesting if you wanted to look at it. So now we're going to go into live demo. So I'm going to be using a programming language called R. There are other ones available. I like R. So LS, I don't have any data in here, so turn in. Is the arrow is basically assigning a variable. Read training.csv. Now what's really cool is if I want, you can show me basically the columns. Me a little bit about it. And more amazing is it can give me a summary of the different values. So what it's basically saying, so it's giving me the minimum value, the maximum value, and the mean. I'm sorry that it's cut off. But it's almost instantaneously, even on lots of large data sets, it can. That's the standard deviation. So what I'm going to do is I'm going to read in. So what I've done is I've separated the data into two files, a training set and a test set. So about 80% went into the training set, and the other 20% were reserved as a test set. So the idea is I'm going to train the model on 80% of the data and use the other 20% to figure out how it did. Really, the are roughly similar in the two sets. So it has 1,200 examples. Which has 4,000. So just like this is like a use statement, but it's done since I'm sort of an interactive shell. It's going to load Cubist for me, and if we wanted to, so I'm going to create a model. Sorry, I thought it would just. almost instantly. No, I thought I excluded it. Did I include it? Yep. Yeah. 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 Yep. Yep. That's okay. No, thanks for catching that. So now let's do predict. %. So correlation is one way of how well the model's doing. It ranges from 0 to 1. So 0 is no relation and 1 is perfect. So this one's actually doing pretty well. Another way of evaluating is what we're going to do is we're going to take the difference. Sorry. So we're going to take the absolute value of the difference between the predicted values and the actual values. So on average, we're about $7,200 off of the actual assessed value. You guys want to ask questions about this? Does what I just did make sense? Okay. Okay. Yeah, exactly. So basically, on average, we're about $7,000 off. And if we wanted to dig into it, we could sort of figure out which ones are more off than others. And it depends. Also, the correlation depends on like how precise. If you're say you're manufacturing like centrifuge pieces for a nuclear reactor, you're probably going to want to have a much higher threat, or like O-rings for a space shuttle. You have a much higher tolerance for what your correlation should be. Whereas if it's like maybe predict, I know it's important to be able to predict the right advertisement for somebody. There's less sort of riding on that. So we can also look at so this is, what's really cool is that I want to show you some of the rules that this created for itself. So rule 3 is that if the neighborhood code is less than 8, the lot size is greater than 75, and the 95, then this right here is the regression formula for those particular examples. Same thing with rule 4. So it's done this in like 0.1 seconds. One problem with regression trees, I mean, it was sort of model trees and decision trees, is once they make a division, if it's suboptimal, they don't go back and recreate it. They can only make orthogonal cuts. It's probably too hard to explain without a slide for it, but you sort of need a certain shape to your data. But it can. You can set it in one of your variables if you want. You can sort of set like how precise you want it to be, or the number of examples that are necessary to be in a leaf. But it can handle like millions of rows and hundreds of features. And then the other really cool thing is that it tells you how much it used the different features. So basically, it used the neighborhood code most of the time, then the lot size, then the latitude. I can't remember what I did with X, and then the lawn. So, and it already gave me the correlation. So, yeah, I think you're right. Yeah. Yeah. I might have had an extra column in my CSV, so I'm going to peek at that right now. I might have had an extra variable in my CSV. The correlate before, but let's take a look at the data to see if I did that incorrectly. Oh, okay, so that's the row ID. So let me just do cut dash F. Yeah. 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 So let me just see. Sed dash n 1p train.csv tr. I'm a command line geek. Sed dash 7 sd comma train. There we go. Okay, so that looks a lot better. Do you guys want me to redo this? Okay. Okay. Thanks. Yeah, I mean, it was about 96 when I did it before, so it would be, but I guess I ran it before and it depended a little. I got one once depending on how I split it. It was around. Yeah, 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 yeah. So it's actually kind of, yeah, yeah, yeah.
I'm interested in, you showed a graph before that showed the land values having sort of a line, the different linear factors
Yep.
smaller than when they were bigger.
Yeah, let me get that one.
Yes.
Yeah.
So I mean, there's sort of, there's a first slope before one, and then after one, there's a different slope. Can you limit the size of the data or somehow work with it?
You can, but what's actually really cool is in one of the rules of like 0.85 acres. What the town does is up to 0.85 acres, they have the steep slope. So now if you have more than 0.85 acres, then the law. So you could limit it if you want to, but it's one of the rules that the decision tree algorithm was actually able to find that cutoff point and have different regressors for the steep slope point than the other one. So, do you guys? Okay. Do you guys have any other questions before? Questions are right. Yep.
I don't know if you can hear me, but decision trees often have a problem that you can easily overfit to your training data
Yep.
and get what looks like perfect results on your training and horrible results on the test data.
Yep.
And so there are algorithms like pruning and whatnot to improve that. Are there similar things for the model tree that you're demonstrating?
I mean, I'd recommend just sort of having a good test set. If you rely too much on your training data, like I'll do this also. Like it'll sometimes run some of its own examples from the training set back through the model that it creates, and it'll seem really good. And you'll go to the test data like you're saying. So I think it's less a function of using the algorithm itself, but just more reserving enough data for testing. You get a 10-fold cross-validation, where a 10-fold cross-validation is where you divide your data, your training data, into equal parts with relatively even distributions, and you run each of the 10 against the other 9. You sort of aggregate the results. So that's a way of using your, because the problem with using training data, splitting off test data, is then you have less real data to train with. So sort of like this sort of balance between how much you want to split off. But I just recommend making sure you have a good enough test set to catch that. Yeah, yes, yes. So here, so anyway, so couple. Let's see if I got this one right. So this one, so we have basically what I did was I gave the happy couple a ID of 1 and then a latitude, sorry, the person, so I have that X in there again. So it's the latitude of 72, longitude of, sorry, parcel ID of 72, latitude of 34.8, longitude of 99.7, and a neighborhood code of 7, and a lot, say they have 2.5 acres. So, I'm just going to include the X because I did it before. Actually, it's sort of everything. Oh. Sorry. What? Sorry. Yeah, oh, thanks. Yep. Oh. Yep, 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 yep. I'm just going to do it. Okay, so happy to. One, two, three, four, five, six, two, three. There we go. So it thinks that their land's going to cost about $400,000. Yeah, 2.5 acres in neighborhood 7. They're allowed in law. So, yeah. You get a paycheck. So, go through here. So, okay. So in terms of reflections, I'd like to reflect a little bit on what we went through. Is there sort of a Zen aspect to data analysis? As I mentioned before, there's both sort of an analytic going towards, and there's sort of a receptive side to it. There's a book, Zen Mind, Beginner's Mind, and the idea is, yes, you do know things, but the answers come to you in the end, I think, as a data analyst. And I like that it combines both sides of the mind in that way. In a similar way, there's sort of a balance between if we're so focused on where we're going, we might miss an important turn that we didn't think about. But if we're also sort of a little too loosey-goosey, we might not get to the actual destination. Is Perl a good language for machine learning? And I think, what do you guys think? Yeah, yeah. I did use R, but there's a New York Times article where there's a huge need for sort of data plumbers, people that sort of get data ready for analysis. And I think Perl is an excellent language for that because there's a lot of unseen work that goes in to getting the data ready for the machine to train on it. I almost think of like the data scientists kind of like gem cutters. There's a lot of work getting the stone out of the earth onto their workbench. So Perl is an excellent, excellent language for that. Also, as I think one excellent thing about Perl is at my first YAPC in Austin, one of the things they really drove home was that Perl is more than a language, it's a community. And I think more than any other programming language, Perl really embodies both sort of our license. So I think there's really a good blend here within our community of the mindset needed for data analysis in terms of both rigor and freedom. Lastly, in terms of if you wanted to start growing, one of the best things to do, I think, rather than starting with a question, I think it's better to start with a subject that you're interested in and then ask questions about that data. Sticky notes, they weren't trying to create sticky notes, they just made a glue that didn't quite work. Out what they do with it. So I think it's a lot harder to get data than it is to get data and then figure out what's going on with it. So I think I'd find a subject you're interested in and then find data about it and just start exploring it. That's the seed or the germ that's going to take you the far. Any book or any algorithm, your interest. Sometimes you'll hit roadblocks, and if you're excited about your subject matter, the same way we all learn programming, you learn to analyze information by analyzing information. And if you think you're working on a subject that you're interested in, your itch to scratch, you'll go a lot. In terms of books, I use machine learning with R. I really liked it. It's a little bit out of date now, so hopefully they'll release a new version. There's also data mining, which is different. It uses a different package called Weka, and then predictive modeling. Videos, I don't know if any of you know Jeremy Howard from Perl 6, but he's gave a wonderful TED Talk on the terrifying and wonderful implications of computers that can learn. Data, as I said before, you need data. Kaggle is basically they're trying to turn data science into a competition. So they provide data sets and anybody can compete, kind of like America's Got Talent. And sometimes if you win, there's a bounty. And there's a lot of good information going on in the forums. So Kaggle's a great place for data. Governments have tons of data, whether it's a federal government, your local government, transit times. Why you live in Boston? Why is the train not? A lot of this data. So government websites are great. There's also repositories of information, and even your own life. You can take your blood pressure and your temperature every day, even on your computer. It's generating tons of network data, and that can be kind of analyzed. So data is basically all around you. In terms of people, one thing. Science is not the lone genius and like Andrew Wiles, figuring out Fermat's last theorem. It's really a social enterprise, and whether it's your coworkers or meetups or conferences or forums, this is really iron sharpening iron, and being around other people that are doing the same thing is helpful. Thanks very much. I'm going to run through my. So, yeah.
Machine learning to be able to say, well, when this happens, then this happens later on, or when these things happen, this one doesn't, right? Like, is that the unstructured machine learning?
No, unstructured is more when you're trying, like, I don't know if anyone has children and you watch them learn, sometimes in the beginning you're sort of like A is different than B, or A and B are similar to each other, and then later to them. So unstructured learning more tries to find like clusters in the data, like these things are similar to each other. And then it's up to the human, like in one of the MOOCs, there's a classic example where if you plotted the weight of coins versus their diameter, and you didn't know which the nickels were and which the dimes were, you'd get a kind of an interesting structure that you could then say, okay, it looks like this cluster. They could say, these are clusters. I don't know what they mean, but these groups are similar. And then the human could go back. So you could just have so you're trying to make a machine that knows what nickels and dimes are. Rather than having to sort everything out ahead of time, these are dimes, these are pennies, you could just feed it all of the coins, get some clusters, and then say, okay, these are probably, you could save yourself some time by then going back and saying, these look like pennies because they're sort of small diameter and small weight to sort of get. That's unstructured, that's unsupervised. Yeah. Yeah, the one problem with real-time learning is updating the model. And also, what do you use? Do you use your own data to retrain it? If so, you're creating a tautology. But at the same time, what other sources do you have? So one of the hardest things, first of all, with online, you usually have a much lower threshold for how quickly you have to respond. And you also really need to think through, like, how do you retrain your model? Like, retrain your model, because as we've been talking, are static. But like in my work, in terms of fraud detection, the function that you're trying to map is actually changing over time. So you sort of have to think like, how do you retrain your model to keep up with the patterns if they're like people's buying habits. People's buying habits are going to change over time. So if you have a static idea of what someone's buying patterns are, how do you update that so that you can continue serving relevant ads? Time. Is there any other questions? I can stay after also. Great. Thank you all very much. The last thing I want to leave. Oh, thank you.